and welcome to our next video, the nature of natural variability, and here we're going to look at dummy variables. So, introduction. The residual variability is our variability that is left over. We want this to be purely natural variability. However, it's usually, well, almost always, going to be a mix of natural variability and unaccounted for variability. Unaccounted for variability is that variability that could be accounted for by unmeasured variables, but is not. Either because we don't have a variable that explains it, that accounts for it, or because we haven't put that in the ANOVA or investigated that. We don't know if our residual variability, the stuff in the residuals, that leftover variability, we don't know if this is just natural variability or if it has some variability that could be accounted for by unmeasured variables. I'll give you an example. Let's say that we were looking at yield, and we're looking at yield and we've got all of this data. We've got different varieties, different soil types, different regions, and we can see that these all affect yield. These all account for variability in yield. But what we can't see, or what we also see, is that there's loads of residual variability left over. We've exhausted all of our variables in our data. And so there's more variability there. This is what we mean by unmeasured variables. Perhaps we don't have data on the rainfall, on the sunshine hours, bits like that. Maybe there was one crop was by a river, and so that reacted differently to another crop, which was at the other end of a field. This is our natural variability, but also in there, things like your rainfall, your sunshine hours is variability, which is an unmeasured variable. We could account for it if we had that data, but we don't. We want to minimize the amount of unaccounted for variability. Generally, that means we want to have in our data all of those kind of variables that you need to minimize it. But this is obviously not always possible. You might be able to get that data from other sources and feed it in and look at it that way, talk to experts and things. But this is just what we mean when we say this unaccounted for, or this unaccountable variability, or these unmeasured variables. So we can create a dummy variable and add it into the ANOVA. This is just a way, that we can try to find out. I'll just pop back a page. As we say, we don't know if this is just natural variability or if it has some variability that could be accounted for by unmeasured variables. How can we find this out? Well, this is a little trick to find it out, and a way that we can look into that nature of the natural variability. So let's say we create a dummy variable and add it into an ANOVA. A dummy variable, just while we're here, is a kind of variable which, in this case, that we're just kind of gonna make up, as it were. We'll dig into this with an example shortly, but it might be that we randomly generate a variable. So we can use the F value to see how the amount of variability that the dummy variable accounts for in the outcome compares to that of the residuals. This is linking into our F value idea that we had in the previous video. We should expect the dummy variable to not account for any variability in the outcome. Therefore, we should expect this F value to be between 0 and 1. If F is roughly 1, then we could be relatively confident that we've probably accounted for most of the important variability. But if F is much less than 1, there may be more variability that can be accounted for. So we'll go for an example. Let's simulate some data so we can explore this. We've done this using R code, and we've given the R code at the end of this example if you wanted to try it out yourself. So here we're going to simulate two variables, variety and fertilizer. We're additionally going to simulate a random variable. This is going to follow a normal distribution and be our natural variability. And this is our residuals. And then we're going to generate yield from this. How we generate yield is that it's correlated with variety and fertilizer. You don't need to know too much. You don't need to worry about these little mechanical things of how the data is simulated. I'm just explaining it in case you were interested. And what is important, is the fact that when we're simulating the data, when we're simulating yield such that it is correlated with variety and fertilizer, and that we are adding in some natural variability. So we can look at an ANOVA with two variables in it, variety and fertilizer. Here's our ANOVA, and we see our F values are very big. Variety and fertilizer do not account for 5.71% of variation in the yield. This is just the difference between our residuals and our total variability, or sum squared, sorry. So we've got 5.71 left to account for. And this is where dummy variables come in. So we create this dummy variable and add it into the ANOVA. This dummy variable is just a variable that we can randomly generate that's not correlated to any other variable. So we can create this dummy variable, and we're just going to randomly generate it from a normal distribution with a mean 0 and a standard deviation 1. You don't need to worry about those sort of logistic things at all. This is just, again, giving a bit more information if you're interested. All you need to worry about is that we create this completely random variable and we add that in. So now we've got our ANOVA, within it our variety, our fertilizer, and our dummy variable. Very unsurprisingly, the amount of variability that the dummy variable accounts for in yield is very small, very, very small. In fact, this is exactly what we would expect, right? Because we created yield we created yield from our variety and fertilizer, and we did not have anything to do with the dummy variable when we created it. If we made this random variable, then this random variable is roughly, should not really account for much variability at all in our outcome. In fact, we'll take this a step further. If we have purely random variability, if we have purely natural variability left that's unaccounted for, then actually our randomly generated dummy variable should roughly account for as much variability in the outcome variable, in yield, as our leftover residual do. Because if what's left in the model is entirely random variability, then our dummy variable that we've created, this random variable that we've created that has no links to our outcome variable, also should account for roughly the same. And we see here that this is kind of what's happened. Our F value at 0.75 is roughly 1. I think I'm getting a bit ahead of myself. There we go. F is roughly 1. So the amount of variability that the dummy accounts for is roughly equal to that of the residuals. We can be relatively confident that we've probably accounted for most of the variability in our yield. So we created a dummy variable to add into the ANOVA, and we saw that the F value is roughly 1. We can repeat this. We can regenerate this dummy variable and rerun the ANOVA. And if we keep doing this multiple times, we'll get a set of F values for our dummy variable. If we then get the overall average of all of these F values, that will give us a better idea of if it's just chance. Again, if F is roughly 1, we can be relatively confident that we've probably accounted for most of the important variability in yield. If f is much less than 1, there may be variability left in yield that can still be accounted for. So here we go. I only ran it 10 times, but here's our 10 different iterations where we regenerated the dummy variable and where we reran the ANOVA. You can see that our variety and our fertilizers don't change on anything other than their F value. And this is because as the dummy variable changes, so does the mean squared residuals, because the residuals are calculated by removing the variability that the dummy accounts for. And we can see over all of this that our F value, it has a bit of a range. So say we were to only generate it once and we got 3.09, then we might think we might be a bit more confused than if we only generated it once and we got 0.003 or 0.002 as we do on iteration 1 and iteration 10. I think we have very low. There it is. Yeah, very low. So if we were to generate it and we had this F value virtually 0, we might incorrectly think, okay, in this case anyway, for this example, we might then think, okay, there's more variability that can be accounted for in my yield. When actually, if we're just randomly generating variables, it's all to random chance. And it could have just been, no, that those randomly generated variables just happened to be a very low value. So I really recommend that you repeat this multiple times and you just find the average of them. And when we do this here, we find, well, as I said, the F value is ranging from 0.002 to 3.10. It shows the importance of repeating this approach to get the average F value to conclude from. Of these 10 variables, of the 10 randomly generated, of the 10 dummy variables, once we put it in the ANOVA, the F value was 0.99586. I mean, I was shocked how close that was to 1. I was very thankful that it's proved my point so beautifully. And so on average, we have that our F value is roughly 1. And if we remember, I just pop back a page. If F is roughly 1, oopsies. If F is roughly 1, you could be relatively confident that you've probably accounted for most of the important variability. So here's our R script. And you can just take this and run it in R if you're interested, or in R instat in the script window. Just the important thing that I wanted to point out here is that this first row, this first line says that we set a seed, and we set the seed at 10. Okay, this means that if you were to run this as well in R or R instat, or you can always translate it to another software language of your choice. I find tools like ChatGPT, you can often give it some code and ask it, okay, can you give this to me in Python code? So you might be able to read the script into ChatGPT and ask it to put it into Python code, and then you can run that in Python, or whichever software is your software of choice. But sorry, the key bit that I also wanted to say here is that we set the seed to be 10. Now, by setting the seed at 10, this means that you will get the exact same results as I did when I ran it. So you can set the seed to be anything you like, or you can remove set seed completely and just keep running it and see what different things come out. These final 2 lines here was where we create the dummy variable and fit the ANOVA to it. And so you can just keep running those 2 lines and you can keep seeing how that F value in the ANOVA changes. Maybe even calculate a mean F value after running it 10 times or so. The mean of the F value should be approximately 1 in this case, because all the remaining variability is natural variability. And we know this because we've simulated this data. Or, sorry, because we simulated this data, I can confidently say that should be roughly 1. With real world scenarios, you can't confidently know that. And that's why you should repeat it, and you can then from there infer what's going on. So let's take a second example. Let's say we just put in variety in our dummy variable into the ANOVA. Now we know, because we simulated this example, we know, like as in me and you know, that 2 variables account for variability in the ANOVA, variety and fertilizer. Therefore, not all variability is accounted for in this ANOVA. Because we're not going to be putting fertilizer into our ANOVA, and we know that this accounts for a large amount of variability in yield, then not all variability will be accounted for. So we should expect a very small F value. And we do, and we get one. We get a very small F value. This is completely as expected because we know that we are missing a large amount of variability. So we are missing, sorry, this is very small, which is as expected because we know that there's a large amount of unaccounted for variability in our residual sums of squares. Now, if you want to, you can go back onto those F value slides for a bit more on this, but this basically implies that there's more variability that can be accounted for. We'll now just look at different dummy variables. So again, this isn't anything you need to worry about as much. This is more just if you wanted to try some bits out. So we said before that we created this dummy variable and that we created it from a normal distribution with a mean of 0 and a standard deviation of 1. You don't need to worry too much about that. But just if you wanted to try things out, then you could see, okay, what happens if we change that mean? Not much would happen, spoiler alert. And what happens if we change that standard deviation? Well, that's going to be a bit more interesting. You can also try repeating the code given, changing the dummy variable values. You could try creating lots of different types of dummy variables and compare them to the residuals. Is the sum of squares roughly the same for the dummy variable as the residuals? I don't mean the sum of squares there, I mean the F value. Is the F value showing? Is the F value roughly 1 when you look at that dummy variable? You should regenerate your random variables multiple times, however, to really ensure that you are certain that the remaining variability is more or less natural variability. We recommend trying this out with simulated data to understand more and more about it. Here's some ideas with, again, some R script attached. So in the first one is just what we did in our example of normally distributed with a mean 0, standard deviation 1, but you could try increasing that standard deviation. So here it is 5, or you can try it as a factor. So just A and B as your 2 options and putting them into C. How does that change it? Thank you.